All right, this is the second part of chapter 7 about electrons and things, and we're going to get back to electron configuration. There are 3 rules about electron configuration, and you have to kind of know the names of them and what they say. So the first rule is the Aufbau principle. Aufbau is German, which means building up. And what it means is when you are filling the orbitals with the electrons in an atom that has a bunch of electrons, not hydrogen, you're supposed to put the first electron in the lowest energy orbital and then slightly higher and slightly higher and slightly higher, so you build it up. You don't just kind of sprinkle them into random orbitals as you feel like it. So that is the Aufbau principle. The order that they go in is the order of energy. And as we were talking about before, with hydrogen's orbitals, they're all if it's all the same n, like if it's 3p or 3d, then they're degenerate, so they're all the same energy. But with polyelectronic atoms, you've got they're slightly out of order. And so what you end up with is 4s is actually lower energy than 3d. As it sticks down, and this is due to something called the penetration effect, which is, let's go to the graph. There's the graph. All right, this is a graph representing your 2s orbital here with the woo, and the 2p orbital with the single yellow spike. And what this is showing is that this is kind of the location, the probability location of the electrons in a 2s orbital. What this is showing is that there is a small hump of probability quite close to the nucleus, and then that probability goes to 0, which actually forms a node, which is the kind of stripy effect that you see if you see a cross-section of an s spherical orbital. And then the probability goes way up, and that's where the majority of your electrons, most of their time is spent in this area. And so you can see that, that part of the s orbital is higher up than the 2p, but there's this little hump down here, so it's penetrating towards the center here. So the 2s orbital is lower energy than 2p. Due to this penetration effect, and the same goes for, that's why 4s has got a bump lower than 3d does, and so it ends up being lower energy. I showed you this, remembering the order thing, 1s, 2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, etc., with the diagonal slashes, and your G's start over here at 5G. And actually there's supposed to be a 7D and a 6F and a 7F. These are all of the excited orbitals, but these are the ground state dudes here. So that's your Aufbau principle. All right, now for the next one, the Pauli exclusion principle. When you draw your electron configuration lines, you know how you can only put 2 dudes in each one. You can't put more than 2 into a single orbital. There's only room for 2. The Pauli exclusion principle says that you cannot have the same 4 quantum numbers for 2 different electrons. And so what that ends up meaning is if you've got like a 2p here, you can have this one, which is -1, 0, and 1. This one and this one, they've got different quantum numbers. You can stick another one in there because it can have the different quantum, the 4th quantum number, +1/2 and -1/2. But if you stuck another dude in there, like like that, then he would have the +1/2, the -1, the 2, and the 1. So you can only fit 2 in an orbital because you've only got 2 options. So it excludes other things. So the Pauli exclusion principle. So Aufbau, you've got to build from the lowest energy up. Pauli exclusion, you can only fit 2 dudes in one orbital. Hund's rule kind of says you want lowest energy? I'll give you lowest energy. Unpaired is lower energy than paired, so if you can manage it, do that. And that's where this thing comes from, where if you're doing like a D, let's say you're doing 3D, you go like this, 1, 1, 1, 1, 1, and then you go back and force them to have seatmates, like so, as opposed to filling them like this. That is bad. The reason that doesn't work is because putting these two electrons together when they could be separated kind of violates the idea of electrons are all negative, and so if they can stay away from each other, they do. So there's a repulsion between these two that is strong enough to separate them into different orbitals until you have to go and jam somebody in there with this guy. So that's Hund's rule. And let's see, if you remember valence electrons, they are the outside ones. They are the ones that contribute basically all of the behaviors to different elements, because the elements are working on fixing their valence electrons up the way they want them. So if you have, for example, an electron configuration that goes, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 10, and 4p4. The valence electrons are the ones that have the highest n. So that's these guys and these guys. So your 4s and your 4p are in that outer shell of n equals 4. So this element has got 6 valence electrons. I know it's sort of tempting, you want to throw those in there, but that's in the third level, so they are actually interior to these 4s, even though these guys have got less energy than them. They're physically smaller, and then the 4s is physically larger but with lower energy. There are 2 exceptions. Actually, there's a bunch of exceptions in the transition metals and in the lanthanides and the actinides, because the way that the Ds fill is not as reliable as we would hope, and the ways the Fs fill is crazy. Because what you're doing is you're cramming all these electrons into an interior shell. And so they're not really valence electrons, and you're just kind of throwing them in there, and so they're sort of funny. So when you actually look at the listed electron configurations for a bunch of those metals, you're like, wait, why is that S1, and then you haven't finished the D, and so they're sort of funky. You don't have to memorize those. There are 2 that you should be aware of that sort of follow an interesting pattern, and apparently they're still arguing about why they do this, but hey. But because copper and chromium are really common, where did my periodic table go? Because they're really common elements, chromium here and copper here, it's sort of important to know what their electron configurations are doing. And what's interesting is that copper is 1 shy of a full D. And so copper sort of cheats, and he's like, I would really be happier with a full D than with a full S. So he snatches one off of the 4S and sticks it in the 3D, which works because the 4S and the 3D, they're so close in energy anyways that it's not that much of a difference for that electron to be pulled over to the D. And chromium does a similar thing, but he's a half full. Chromium is almost to 25 here, which is 3D5, so he's almost got his D half full, and same kind of reasoning with copper. So he snatches one off of the S. And so you end up with this. This is not an excited state. This is the normal state for chromium and copper. And then below them in the rest of the transition metals and stuff, it's ridiculous frequently. All right, so that's electron configuration. Now we're going to do some periodic trends in atomic properties. And the first one we're going to talk about is ionization energy, and then electron affinity and atomic radius. Electronegativity is in a different chapter, so we're not doing that one right now. All right, ionization energy is the amount of energy that is required to pull one electron off of an atom. And you can compare how much energy is required to pull electrons off of different atoms. That sort of gives you an idea of what those elements are like and what their properties are and what they have a tendency to like doing and not like doing. For example, it's really easy to pull one electron off of an alkali metal because they didn't want that electron anyway. It does take a little bit of energy because you are separating a negative and a positive, but it's not very much. It is very hard to pull the last electron off of a noble gas because they're happy the way they are. They don't want to be messed up. You can see when you look at the trends that if you have kind of the whole periodic table filled out with our first ionization energies, it's high at the top. So up here, your ionization energy is higher than it is down at the bottom. And the reason for that is because your electrons are physically closer to the nucleus when you're up at the top. And so there's more effort to pull that negative away from that positive. You've also got it higher on the right-hand side. And the reason for that, it gets into a couple of important vocabulary words. Let's say we're talking about the second period here. So in the second period here, you've got your ionization energy increasing as you move across to the right. And the reason for that is because when you're moving from lithium to beryllium to boron, you're adding a proton and an electron every time you move. And every time you add a proton, you're increasing the charge of the nucleus, which is making it harder to pull those electrons off. And yes, you're also adding an electron, but those electrons are all in the same shell. And so they're not really shielding you from the charge of the nucleus. You would get better shielding if you had like a whole shell in between you and the nucleus. Because these electrons are being added to the same shell, they don't provide enough shielding to counteract the effect of the additional proton as you go to the right. So as a result, you end up with really high ionization energies in the top right-hand corner of the periodic table, and it kind of gets lower as you go down to the left. That's your first ionization energies. You've also got, you can keep ripping electrons off. Hey, why not? We did one, why not 2, 3, 4? And that can provide some interesting information about kind of where on the periodic table your element is. Because, for example, for lithium, your first ionization energy is pretty low because it's got that 2s electron all by itself. You can pull that off. It's not so hard. After you've pulled that one off, you have got a positive lithium ion with a complete shell. So it has an electron configuration similar to that of helium, but it's also positive. So if you go and try and pull off the second electron from lithium, it's like, I do not like that at all. And so it takes a lot of energy to rip off the second electron. And you can kind of work that out because, well, the first one was easy, and the second one, there was this huge jump up to a much higher amount of ionization energy. Whereas, for example, you might see with like boron, you pull one off, that gets you to beryllium's electron configuration. Okay, You pull 2 off, it's a little bit harder because you're pulling it off of a positive ion. You pull 3 off, it gets you down to helium's electron configuration. If you try and pull 4 off, that is going to be very hard because you're doing it off of a seriously positive ion with a happy electron configuration. So you kind of see the numbers increase. And so that gives you a clue if they say a mysterious element has these ionization energies, which one is it? You can sort of figure it out. All right, that's ripping one off. Haven't you wanted to jam one on? I mean, why not? So I've just noticed that this is too wide. So let's see if we can do something about that. Can you hide now? These are gone, okay? Just pretend that you don't see that.
Right.
Okay. So for electron affinity, that's the energy that if you cram one electron on, the majority of these elements here will give energy off. This is the opposite of ionization energy, which is the energy required to rip one off. If you jam one on, sometimes that's exothermic. Sometimes it's not, which is kind of cool. And there are reasons for each of those. So when you look at the little graph in your book and you kind of guess, you end up, it's not a very quantitative graph, and so I kind of figured out what the electron affinities were and wrote them in my notes here. So let me copy down. We've got -90, -70, -70-ish, -50. This element, beryllium, and this element, calcium, magnesium, they do not exothermically receive an electron, so they actually don't have an electron affinity value. This one barely does. These guys, the noble gases, also do not exothermically receive an electron, but boy, let me tell you, the halogens sure do. And these guys do to some extent. Nitrogen doesn't care for it much, but this one will take it if you make him. And these guys don't really like it much either. So what you end up seeing is that when you add this electron, if it finishes filling something, it's quite exothermic. So with the halogens, it's very high with the halogens, the electron affinity. And we kind of knew that. That represents, halogens love getting one more electron. To some extent, these guys also. This one is interesting because nitrogen is like, no, sorry, I don't really want one more. And that makes sense because he's half full. And so he's like, I'm actually sort of more stable as I am, thanks. So nitrogen doesn't care for it. These guys, carbon, they sort of like getting one more electron because it gets them to the half full state. And these guys don't mind it much either because it gets them to the full S. The alkaline earth metals don't care for it because they're at a full S, and then you add one more and they get over here to lousy territory. So it's kind of high in 3 places: when you fill your S, when you can half fill your P, and when you can fill your P. And they're all negative because it's exothermic, so the energy is being released. So that is electron affinity for you. In general, as well, it's supposed to be higher at the top. Yeah, there's a lot of variation with that, but it's because, again, the electrons are being put closer to the nucleus. All right, so there's that. and atomic radius. You guys remember atomic radius? That is the size of the atoms, and we're going to flip to our periodic table again to talk about that. Obviously, hydrogen is a really small atom, and ununoctium is really big. We already knew that. But there are a couple of trends. From top to bottom, if you don't know that they're bigger at the bottom, I don't know who you are. They've got more things, they're bigger. And if you're going to actually talk about that intelligently in some sort of essay type thing, you would talk about the value of n and the radius of the increasing shells of electrons. Because don't tell me that it's big because of the nucleus, because the nucleus is teeny weeny tiny in the middle, plunk. And then the size comes from the electron shells. So, you've got your 7s electron shell here. That's pretty big. It's not actually this big because atoms are really small. So, point is, you increase atomic radius as you go down. As you go across, you're thinking, I know what you're thinking. You're thinking, they get bigger. They don't get bigger. They get smaller. But that's weird. Yeah, I know. But again, as you go from left to right, you're adding a proton, an electron. You're adding a proton, an electron, a proton, an electron. And again, you've got the effective nuclear charge and the shielding thing coming in. As you add a proton, that proton is positive, the electrons are negative, and so it goes and sucks them in just a little bit. Yes, you did add an electron, so there's a tiny little bit more shielding. But again, it's all in the same shell, and so it's not super effective. Shielding is effective in extra shells. So your effective nuclear charge, which is basically how strong am I feeling the pull of the nucleus right now, goes up as you go to the right, and so atomic radius decreases to the right. What that means is that atomic radius is really big in the bottom left-hand corner. And I think that's all we need to talk about for atomic radius. Oh, no, we should talk about ionic radius too. The same sort of reasoning works perfectly well when you get a question like, what is going to happen if you compared this ion with this atom, this neutral atom, which one is going to be bigger? You need to think about, well, does this ion have an extra electron that bumped it up a shell? Did it lose its electron that was bumping it up a shell, and so now it's shrunk down so that it's the size of this guy? So you need to consider kind of what has happened to the electron configuration of the ion to kind of be able to compare it to the neutral atom. All right, the periodic table. Why are we talking about the periodic table now? It's kind of random. Is because Mendeleev made observations and said, we should make this table because then everything will be listed in order and it'll be great. And so you have this periodic table, and for a really long time it existed, but people didn't understand, okay, so the properties are the same as you go down, but why? What do they have in common? What is it that causes all of this grouping into families and properties and junk? And that is related to electron configuration because it's the valence electrons. These dudes, the alkali metals, what they all have in common is that they have, their valence shell has one electron in an s. And so they're liable to do the same kinds of things in order to fix that. They react very similarly. So that's why we're talking about the periodic table now. You do need to remember the names of things, but come on. Alkali metals, alkaline earth metals, halogens, noble gases. Here are the nonmetals. Here are the metals, is everybody else. Your metalloids are except for aluminum, and the lanthanides and the actinides. So you do need to know the names. The families or groups are up and down. The periods are left and right. And one of the things that they kind of use as an example of, see, here is an example of, there are a bunch of properties and you can watch trends of all these different properties because these guys are related to each other. The book talks about the alkali metals as an example of, see, look, their valence electrons are similar, they have properties that are similar to one another, and they have trends and neener. So let's talk about the ones that they mention. The melting point decreases, the boiling point decreases. It's kind of a nice smooth transition. Okay, whoop-de-doo. These two need a little bit of explaining, the reducing ability, because I don't think that we talked a lot about oxidation and reduction. And now I'm going to. So you need to remember the silly acronym Leo says GR, which obviously Leo is a lion, and lions, they say GR.
Grr.
You're not a lion. So what this is loss of electrons is oxidation, but gain of electrons is reduction. And that helps you remember that if you lose an electron, you have been oxidized. If you gain an electron, you have been reduced. And the part by reduced, they mean the charge has been reduced. So if you get a negative thing, now you're -1. So your charge has gone down. That's sort of screwy because we don't think about gaining negative things very often. And that's why the lion thing helps you remember it. I kind of have to refer to the lion every time. So what do these guys like to do? Do they like to be oxidized, or do they like to be reduced? Well, you say to your brain, I know that what they like to do is lose that one stinking electron. Loss of electrons is oxidation. They like to be oxidized by 1. You can also think of it the other way. Yay, because right now all we need is also the ability to flip it backwards, which is they like to be oxidized, but that means that they like to reduce other people, which means that they like to give other people their negative charges. And so that's what they're talking about here. Reducing ability increases. But it's important to remember that what they're talking about here, the reducing ability, is when you're dealing with a regular reaction that is not taking place in aqueous solution. So, for example, if you are talking about sodium reacting in a chlorine gas environment, that's the type of reaction that has got this trend here, the reducing ability increases. So, for example, potassium would do that much more energetically than sodium would. In contrast, and flipped backwards, because that's what we need, is when you have reactions that happen in water, they sort of found it to be a little bit weird, but actually the guys at the top were better at reducing the other guys than the guys at the bottom. And so that was confusing until they figured out, well, the reason is because they're in water. And what you end up with is the hydration of the ions. If you've got lithium ion like Li+, it gets surrounded by the polar water molecules, the little negative ends of the polar water molecules, and that's very exothermic. And because lithium is so densely charged, the water molecules are like really into it. Because he's really small and has a positive charge as opposed to cesium, which is kind of a big fat dude, and he has one positive charge. And so because it's more exothermic with the hydration, you get more energy in aqueous solution for the top guys, and so the reduction goes better with him than with him in water. But the reduction goes better with cesium compared to lithium in general. The reason for that being, which I forgot to mention, is that the electrons are farther away. So it is easier for cesium to reduce somebody else and kick off his electron compared to lithium in general, because his electron is way out here and lithium's is closer in. And that is the whole lecture, except for the problems. So now take a moment, go do your problems on the back of the sheet, and I will be back and doing them for you. And we're back, and here are your problems. 1. The ground state electron configuration for vanadium is, well, I don't know, where's vanadium? Here he is, right there. So that's going to go all the way up to the first d orbital, which I happen to know. It goes like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d. Was he number 3? Yeah, 1, 2, 3. 3. Bam. There you go. That's that one. An excited state electron configuration for fluorine could be, well, where's fluorine? There's fluorine. Goes up to 2p5 in general, but he's excited. So 1s2, 2s2, 2p. So let's say one of his 2p electrons got excited. So he was going to have 5, but now he's got 4. And what do you suppose he's jumped up to? Maybe he got really, really excited and he's at like 5G or something. Whee! Okay? Could be really anything above the energy level 2p. Alright, ionization energies for an unknown element X in the third period. That's this one. Are 580, 1815, 2740, 11,600, and 14,800. If you look, you can see that there is a gigantic jump, and it's right from there to there. So that means taking off the first one took some energy because you're pulling it off away from the nucleus. Taking off the second one took a little bit more energy because you're taking it off of an ion. A little bit more energy because you're taking it off an ion. And this was ridiculous. So that means that the fourth electron that you pull off is quite unhappy. So let's go and see who qualifies for that in the third period. So in the third period, sodium would be happy with 1 coming off and then would get crazy when 2 came off. Magnesium would be okay with 1 and 2 coming off, but not 3. Aluminum would be happy with 1 coming off, 2 coming on. He'd be sort of happy actually sitting at magnesium. Magnesium's got a good deal, but he'd be happy with 1 coming off, 2 coming off, 3 coming off, and that would get him to neon's electron configuration. That's the big jump. I'd say this sucker is aluminium. All right. Why is it more difficult to ionize nitrogen than carbon? Well, if we remember ionization energy, we're talking about taking 1 electron and pulling it off. So let's go look at their positions. The periodic table, here's nitrogen and here's carbon. Pulling 1 electron off of carbon is going to get him from his electron configuration to boron's electron configuration. Nitrogen has sort of a semi-decent position because he's got his 2p orbital half full. So the reason that it is more difficult to ionize nitrogen than carbon is because nitrogen is in a semi-stable state with a half full p orbital, whereas carbon is not. I'm not going to write that down. And what would have a larger radius, a bromine atom or a bromine ion? Why? Let's go look at bromine. Hi, bromine. There's bromine. When bromine becomes an ion, typically the ion that it becomes is bromine -1. He hops over and gets an electron configuration with 36 electrons. Is that going to make him bigger or smaller? will, typically when you're talking about, say, bromine versus krypton, krypton is smaller because the extra proton pulls the electrons in. But when you're talking about bromine versus a bromine ion, there's no proton that changes, just the electron. So adding one electron onto bromine, you're going to have slightly more electron repulsions in your 4, your n equals 4 shell. So with the slightly more electron repulsions, he's going to go eep and get slightly bigger. And that is your answer for number 5. And that is it. Thank you. Goodbye.